In this module, we'll review vectors. We'll go over definitions of vectors, what are row vectors, column vectors. We're going to define linear independence, basis, transposes, inner products, lengths of vectors or norms. All of these concepts are going to be needed for doing some of the elementary linear algebra that's needed in this course. What's a vector? It's just a collection of real numbers. You can collect them and put them in a row, or you can put them in a column. So here's an example of a row vector where I've put everything as a row. Here's an example of a column vector. And if you notice carefully, both of these vectors have n components. So we will call a vector to have n components if it consists of n real numbers. A row vector or column vector, and we will denote any of these vectors by the symbol r to the n. R to the n means that every component is a real number, and there are n of them in the place. To just fix ideas, it might be easier to think in terms of R2, which means these are vectors with just two components. And it's easiest to think of these vectors as belonging to a plane. And we are used to calling this plane by the x-axis and the y-axis. So think of x-axis being one of the components of the vector, y-axis being another component of the vector. So let me just give you some examples of vectors that we're going to use later on in this module. So here's one vector. Its x component, or the first component, is going to be 1, and the second component is, say, going to be equal to 2. So that vector will be this vector. At the end of the dot corresponds to a y-axis of 2 and an x-axis of 1. So let's label this as v. This will simply be the vector 1, 2. The first component equal to 1 and the second component equal to 2. Here's another example. The x-axis, or the first component, equal to 4 and y-axis equal to 1. So that's that point, and I'm going to be connecting it with this vector. And in the rest of this module, I'm going to be referring to this vector as w. It has 4 in the first component and 1 in the second component. By default in this course, unless otherwise specified, we'll assume that all vectors are column vectors. That is, all the components have been arranged as a column. All right, so we now know what are vectors. They're collections of real numbers. By default, it's going to be a column vector. Now we want to understand what can we represent using these vectors, what happens with them, and so on. So the first thing that we want to do is multiply these vectors with real numbers and add them up. So v1 and v2 are vectors, and I want to multiply them by a real number alpha 1 and a real number alpha 2, and then get a final vector w. So to give you an example, here's my vector v1, here's my vector v2, and just to fix ideas, each of these v1 and v2 actually lives in r to the 3. Why r to the 3? Every component is a real number, and there are 3 components. So the 3 refers to the fact that there are 3 components. I'm going to multiply them by 2 real numbers. So 2 is going to play the role of alpha 1. 4 is going to play the role of alpha 2. And what do? I take these real numbers, multiply them component by component, and add them up. So in order to get the first component, I take the 2, multiply it to the 1, take the 4, multiply it to the 0. I get 2 times 1 plus 4 times 0 equals 2. That gives me the first component. If I want to go to the second component, then I take the 2 and multiply it to the second component 1. Take the 4, multiply it to the second component, which is also 1. 2 times 1 is 2. 4 times 1 is 4. Added up together, you get 6. You want to go to the third component, the same thing. 2 times 0, 4 times 1, 2 times 0 is 0, 4 times 1 is 4. You get the third component, 4. So when you write a vector w as a combination of two vectors v1 and v2, we're going to say that this vector w is linearly dependent on v1 and v2. Why the linear? Because I'm multiplying by a real number and adding them up. Other words are w is a linear combination of v1 and v2. Yet another word, w belongs to the linear span of v1 and v2. All of these three things mean the same. Linear dependency, linear combination, linear span. Now in the next set of ideas, we'll need a concept of linear independence. When can we say that we cannot write a vector as a linear combination of other vectors? To fix ideas, let's again go back to R2, and I'm going to use my favorite two vectors v and w. So here's my vector v, and here's my vector w. For now, we don't really need what the components are, so I'm not going to bother with that. Now, we want to understand, what does a linear span mean? What kind of vectors can I generate by scaling the W? What can I do by multiplying W by a real number? And you can convince yourself very easily that all the vectors that you can get are going to be on that straight line. When you scale it up, you get by a positive number, you get up the line. If you multiply by a negative number, you go down the line. Similarly, all the vectors that can be gotten as linear combinations of V will lie on this straight line. Now, we want to ask ourselves, can I represent V as a multiple of W? Clearly, that's not true, because I can't, when I scale the W, I get points on this line. V doesn't belong to that line, so I can't do anything about that. Similarly, W is not written as a linear combination of V, and therefore we'll say that V and W are linearly independent. Let's throw in another vector now, X. It's again a vector in R2, and I want to ask myself, is this linearly independent of V and W? Is it possible that X cannot be written as a linear combination of V and W? Again, it's very easy to convince yourself that if you just draw a line parallel to V, you can write your vector X as a combination of vector that starts from the origin, is aligned to the vector W, and comes up to this point. So therefore, this vector is some alpha 1 times W. This vector here is parallel to the vector V, so I can write it as some scaled multiple alpha 2 times V. And because now X is the sum of this vector and that vector, you end up getting that X is actually equal to alpha 1 times W plus alpha 2 times V, which means that X is linearly dependent, LD just for short, linearly dependent on V and W. In fact, we'll see in the next slide that in R2, if I give you any two linearly independent vectors, you can write any other vector as a linear combination of these two. And that set of vectors, say these two V and W, will actually be called a basis. So that's the next concept that I want to learn about vectors. A basis is a linearly independent set of vectors that spans the entire space. Any basis for Rn, meaning a vector which has n components, has exactly n elements. So a basis for Rn has exactly n elements. In the last page, I showed you an example of R2, and this should have just two elements. V and W were linearly independent. There were two of them, and therefore I know that this must be a basis. Now, it will turn out that it's much easier to think in terms of a standard basis. What's a standard basis? It's shown here. It's a collection of vectors such that they have only one of the components, and all the other components are equal to 0. So the vector E1 will have 1 in the first component, the vector E2 is going to have a 1 in the second component, and the vector En is going to have a 1 in the last, or the nth component. Now, if you give me any vector W which belongs to Rn, meaning that it has n components, I can very easily write it as a linear combination of E1 through En. Why? Because in each of these vectors there is exactly one element that's not 0. So if I want to get the first element of W right, I have to take it to be W1 times E1, because everything else has 0 contribution. If I want the second component right, I have to take it W2 times E2, and so on up to Wn times En. And therefore, this basis, I can split any vector W as a linear combination very easily, and we will see that in practice this turns out to be very convenient. Again, to put it in perspective, here's R2. Here's my x-axis, here's my y-axis, and when I showed you in the first slide, x-axis refers to the first component and y-axis refers to the second component. So the vector E1 is just this one. It has one component 1 in the x direction and 0 in the y direction. E2 is this one. It has a component 1 in the y direction and 0 in every other direction. And it's very easy that if I take a vector x, all I have to do is drop it down here, and this length down here on the x-axis is x1, on the y-axis is x2. And it's a very easy way to combine it. But any other set of linearly independent vectors, two of them, will make sure that this is going to be a basis. So again, this was V and this was W from the last page, and V and W is also a basis. This is also a basis, and E1, E2, which are these two special ones, are also a basis. The second basis is special, and we'll just call it the standard basis because it turns out that it's very convenient to work in terms of this basis. All right, so far what do we know? We know what are vectors, we know linear dependence, we know linear independence. We know that if I'm a vector in Rn, meaning it has n components, I can find a basis of n linearly independent vectors such that every vector can be written as a combination of these. So what's the next concept? The next concept that we want to learn is that of a length of a vector. So let's start with the basics and then we'll generalize it to what I want here. So if I give you R2, and let's take a vector which has the x component equal to, let's say, 4, and the y component equal to, let's say, 3. So this vector has a representation 4, 3. Then our high school trigonometry tells us that the length of this vector is nothing but 4 squared plus 3 squared. So I'm taking the x-axis and squaring it. I'm taking the y-axis and squaring it, square root. So that gives me 16 plus 9 square root, which gives me 25 square root equal to 5. So that's nice. I have a definition of length. Now what does this definition of length satisfy? It satisfies several properties. It satisfies that the length of any vector is always greater than or equal to 0. If the length of a vector is equal to 0, then that vector itself must be 0. So you cannot have a vector which is not equal to 0 whose length is equal to 0. And the intuition follows from this triangular expression as well. If I scale a vector by an amount alpha, it doesn't matter whether I scale it positively or negatively. The length just gets scaled by the absolute value. So here's the idea. Here's my vector v. If I double it, I get this vector. If I multiply it by -2, I get that vector. The length of this vector and the length of that vector is the same. The direction has changed, but the length remains the same. That's what this absolute value does. The third one here tells you the relationship between lengths of addition of vectors and the original lengths. And this is known as the triangle inequality. The way to remember this geometrically is that if you've got one vector here, you've got another vector there, the sum of the vectors is this one. The length, this length is always going to be, let's call it L3, is always going to be less than or equal to L1 plus L2. This is the basic geometric fact. L3 has to be less than or equal to L1 plus L2. And this particular fact is encapsulated in this little statement over here. And that's why it's also called the triangle inequality. Now, mathematicians have looked at this concept of length, this particular concept of length that I've been talking about, which is take each of the components, square it, add it up, take the square root. And now they're calling it the L2 norm. The 2 stands for the fact that I'm squaring it and take the square root. And they notice that the properties that I want, the fact that the length is greater than or equal to 0, the fact that triangle inequality holds, the fact that if I scale things remain the same, is true for other definitions of length. Now, since I'm taping this in New York, I'm going to try to tell you about a particular notion of length, which is called the L1 norm, otherwise known as the Manhattan distance. I'm sitting at a particular point here. I want to travel to another point. I can only go in blocks north and south or east and west, and I want to figure out how much do I need to walk in order to get from this point to that point. So I have to walk from this point to this point, and then walk from that point to that point. So this distance is 4, that distance is 3. So the L1 distance, or the L1 length, or the Manhattan distance is 4 plus 3 is 7. The L2 distance is 5, because I can sort of cut across. The L1 distance is 7. L1 also satisfies all the properties of a norm or a length, and therefore it's sometimes convenient to encapsulate all of them as just norms or lengths. For the purposes of this course, we will mainly be focusing on L2, but I just wanted you to know that there are other definitions of length that are interesting and sometimes become important in applications. All right, now we know vectors, we know linear combination, we know lengths. Now we want to get to the next concept, which is that of an angle. And in order to get to an angle, I have to introduce this idea of an inner product or a dot product. So the dot product of any two vectors v and w, so v and w are vectors in Rn, they have n components. So the dot product between v and w is simply going to be taking the ith component of v, taking the ith component of w, multiplying them together and adding them up. For those of you who are experts in Excel, this is nothing but sum product. Take the product of the components and add them up. The sum product function in Excel is nothing but an inner product or a dot product. If you review back into the last slide, we had defined the L2 norm there to be every component squared square root. And that can now be written that the L2 norm of a vector is simply take the vector v, take its dot product, so v dot product with v, and take the square root. So now we want to understand an angle between these two vectors. So to do that, here's a picture. Here's my w, here's my v, here's an angle theta between them. So in order to understand how the inner product relates to the angle, the length of this vector is the length v, the length of this vector is w. So the inner product between v and w simply is take the component of v along w and multiply it to the length of the w. So if you drop down an orthogonal point over here, this component is exactly equal to the norm or the length of v cosine of theta, and that I'm going to multiply with the length of w, and that should give me v dot w, which ends up giving me that cosine of theta is exactly equal to v dot w divided by the norm of v and the norm of w, or the length of v and the length of w. And to emphasize the fact that these are all two norms, I'm just going to put a 2 there. All of that is encapsulated in this slide. Cosine of theta is v dot w divided by v and w, and this is true not just in R2 but in Rn. You can define angles in Rn. I'm going to show you in the next module that v dot w is actually a combination of two operations, the transpose operation and the matrix multiplication operation. But that has to wait until we get to the module of matrices. So that pretty much brings us to the end of the introduction to vectors. This is all we need to know in terms of vectors, and this is all we're going to be using in the course. In the next prerequisite module, the module that comes up next, we're going to review concepts about matrices.